Okay, I think we'll get started. So today we're going to be doing the Arithmetic 1 lab with the PIC10F200. And here we're going to look at how to multiply two numbers. We're going to do a comparison, or basically we're going to identify greater than or less than between the two numbers. And then we'll look at the modulo operation, so essentially finding the remainder of the number. A couple of the big ideas here. We'll be storing some data to the memory. We'll be using what are equivalent to for and if-then statements. So of course in the assembly language, and for in particular the PIC10F200 assembly language, there is no if and then statements. So how do we use it with our normal go to and call and that sort of thing? We'll need to talk a little bit about interpreting the integers that are stored in the memory as signed or unsigned. So we know that the PIC10F200 operates as an 8-bit, up to an 8-bit number, so 0 to 255 if it's unsigned. If you want to include negative numbers, then we use that most significant bit, the 7th bit, bit in 7 position, to identify negative or positive. So if that bit is a 1, then that's interpreted as negative. So really you have from minus 127, I think, to up to 127, 128 in terms of what can be used when we're talking about signed integers. And because of that, this is going to give us a chance to read an individual bit. So we're going to read that bit number 7 in the memory to see if it is negative or positive. And we'll talk a little bit about algorithms, although none of these are really all that sophisticated. Now, none of this involves actually using the PIC10F200 directly, so we're going to just do everything with simulator and the debugger tool for that simulator. So we won't be showing any of the action on the PIC200 for this video. All right, so just basically the program is a collection of these ideas: the multiplication, the comparison, and modulo m. So we're going to just store two numbers. The example we'll start with is we'll put a 5, this is decimal here, 5 and 17 just as some practice numbers. And we'll use this throughout. And then just to show some different things down here in comparison and modulo, we'll just switch these numbers and maybe use a different number as well. All right, so how are we going to do this multiplication? We know with the instruction set for the PIC10F200, there isn't a multiplication. We have add and we have subtract, and we also have the and or operators as well, but we don't have multiplication. So we actually have to use addition to talk about that, and we will actually add the value in stored in register 11, memory register 11, memory register 10 a number of times. So if we're storing 17 in here, then we will take 17 and add it to itself 5 times. And so we have to run through essentially what's essentially a loop, and it's basically kind of a for loop type structure there. Then after this is done, we'll drop into a comparison. And so what we're going to do here is we're going to subtract the value in register 10 from the value in register 11. So in this case, we'd subtract 5 from 17, and we're going to check to see is that positive or negative by reading that most significant bit. Then we'll drop into the modulo, and here what we're going to do is basically, again, we can only use addition or subtraction. Here we're going to use subtraction, and we're going to just keep subtracting the number, this modulo m. So we're going to just subtract m and over and over and over until we go negative, and then we'll add back 1, and that should give us then the correct residue for this calculation. So, for example, if we wanted 17 mod 5, what we're going to do is we're going to subtract 5. That would bring us to 12. Subtract 5. That would bring us to 7. Subtract 5. That would bring us to 2, which would be the answer. But we're not going to be able to robustly check that. We subtract again, that's going to always bring us negative. And based on then going negative, what we can do is add back that 5 one more time to get us back up to 2 and get the correct modulus for this, so the correct residue for this. So let's look at the program itself now, and we'll just go through line by line and we'll see how all this is done. All right, so here's the program, and this is just header information up here. So this is telling us that we're going to be doing these different arithmetic multiplications. This stuff is boilerplate, so we'll talked about this in another video. So all of this stuff just sets up the configuration bits, the include file, tells the program counter where to start, and so on. And I'll swoop down here to the end as well, and we have the end of the end for the reset vector as well. Okay, I'm always going to just leave this boilerplate information here. So we start our program with main, and all this is just to set things up for how we usually want to run our PIC10F200, so to set the different input outputs and other values. So for this particular example, we don't need to worry about this at all. So we'll jump right to the main loop, and I'm going to set a whoops, I can't do that. I'm going to set a break here so that when we run the program, it'll stop here, and then we'll be able to step line by line. So let me go ahead and run the program in debugger mode, and you see it builds successfully. And now we can look at the registers that carry information. In particular, we're going to be looking at the working register here, and then we can also look at the file registers. And so in particular, we'll be looking at memory units 10 or 10, 11, like we talked about on the board there. All right, so let's just step through this, see what's happening, watch things change with the file registers and so on. So this is setting up, this stuff up here is setting up the two numbers that we're going to use. We're going to use decimal number 5 and decimal, or base 10, 17, and 5. So we're right here with the program. So let's look right now at our working register. This, what we can see here, this is just coming off of this stuff from above. So we will step now into the next line, and we see our working register go to 5. Now we're going to move that literal from the working register into the memory. So let's go ahead and go to file register, and we'll pay attention here now to register 10, and we'll jump that in, and we see here that 5 is stored to memory. Then we want to do that for 17, so we have to put that into the working register. Remember, we always have to move things to the working register and then to where we want it to go. We can't combine a literal into right into a memory unit. Okay, so step through here. We've moved now. 17 should be in the working register, so let's check that. So 17 is up in the working register. Go back to our file registers. We're not quite loaded that into position 11 yet, or register 11, and here it comes. So there's 17. Then, probably not necessary, but just clear the working register. So let's step through that. We go back up here, and we see the working register set to 0. So now we've entered our part of the program we're going to multiply. And so we're going to go through this loop 5 times. So we're going to, because we're going to add 17, which is sitting here in memory unit 11, 5 times. Now, notice what we're going to do here is, I guess I should have mentioned this up here. We skipped through this. we're going to want to keep the original numbers for the other things that we want to do. So we use a sort of a dummy register to carry a copy of what's in 10, so 5. So 5 is placed in register 15, so let's confirm that. So 15 here, 5 is sitting in there. But this will now act as a counter. So when we get into the multiplication algorithm, we're going to just add 17 to itself again and again, and we want to count the 5 times, because that's what multiplying by 5 is. So we're going to watch now 15 decrease as we step through this loop. So let me step through this loop, and now 15 has come to 4. Nice thing about, as you probably have noticed already, the nice thing is that the registers change color if they made a change, so very easy to follow. So this is decremented. Now this is decrement this and then skip if 0. Well, it's not 0, it's 4. So that's going to bring us back up to here. And so let's look now at the working register. So nothing is changing up here. These are all staying the same. But if I go to this working register, now I'm 34, because that's 17 plus 17. And we just keep doing that. And so we'll see it go again here now, 51. And we'll keep going through, 68. And let's look now we're down to our last one here. So the next time that's decremented, it'll skip through. So we'll go to our working. Watch our working change, 85. This is decremented. This will decrement now to 0, and then it will skip. So notice here, it will decrement and then check. So we go across. And now we'll move this and store this multiplication result in memory register 12. So let's put that in there, and so here we see the 85, which is the result of that number. Here it is in hexadecimal and binary as well. Okay, so let's go on to this compare unit. So again, we're going to look at our original examples here. So this is the 5, and this is 17. So we're going to subtract now number 1 from number 2. So we're going to subtract 5 from 17. And so let's do that. And we're going to put that in memory register 17 here. So there's 12, 5 from 17. So now we're going to check, this is going to check the 7th bit, so or the 8th one over. So bit number 7, 8th bit over, and so we see that that is a 0. So we're going to, when we check this, skip if set. So it's not set, it's 0, so it's going to go into this function here. So this gets into this call is positive, so that's going to send us down here. So we're going to actually call a function here. And what I just did was I'm going to flag that. I'm going to put the character. This is a chance to use another data type here, a character type. So I'm going to put a capital P into register 13. So we're going to hit the next, and we'll go to is positive, and so let's see, 13. So it doesn't step. I guess it doesn't step through those sections. It went to that function, and then let's look at 13 here now. So 80. This doesn't mean anything here, but here's the P. So we're working here now in terms of the character. So put a P here, and now it's going to check this bit again, and we don't want it to change that to a negative. So here's is negative. All we're going to do is just put an N instead of a P, but it's not negative, so it should skip that. So let's check that, because it skips it because it's clear, and it is clear because the leading 0 here, the most significant bit, bit number 7, or the 8th bit, is 0. All right, so let's try modulo. So 17 modulo 5, so that should be, the answer should be 2. So let's see how that works here. So again, we're going to move this into the working register. So let's check our working register now. So we have 17 placed in the working register. We're going to subtract that number and place it back in the working register. So let's do that. So now we're down to 5. And so this is going to subtract what's in the working register, which is still 5. That's our original number here, but it's going to subtract what's in the working register, but place it back into register 14, not the working register. And then we're going to check that last bit there to see if it's negative or not. And so let's go ahead and do that. So this is not negative, so it shouldn't skip this. So it goes to remove integer, so that just comes back up here. And so let's look at our values here. So working register will stay 5, but register 14 now has become 12. And so let's go back up to register, remove integer. And now we're going to subtract again what's in the working register. So we're not changing the working register this time. We're changing the memory itself. And that's the difference between putting the 1 here versus the 0. And so let's check that. Okay, we've made a subtraction. Now we're down to 7. Still positive, so that's going to not skip this. It'll come back into the loop. We go again. We're down to 2. Now, of course, that's the answer, but it doesn't know that it needs to stop. So it's going to send us through the loop again. We're going to subtract. And now we've gotten a negative number. See, 253. So we've circled around 253. So that's 2. And in binary, that's got a leading 1 here. So that's what's going to be checked here. And so now we will skip this loop. And I don't know if this is strictly necessary. I've had some trouble if I don't put no operations in. Probably not so much in this in this loop here, but certainly in functions. So I think back here actually, yeah. So in the is positive and the is negative from up above, it was important to put the no operation in just to get it to work. I'm not quite sure why that is, but it doesn't work if you don't have that no operation in. All right, so now we should add 1 back because we've subtracted 1 too many. We went down to the residue, then we subtracted, went negative, so we have to come back up. And so that's what's going to happen here. So we come back up. Let's look at our working register. So this should pop back up now. Comes back up to 2, and then that's it. That's our change. So we'll go to the main loop. And now we're back at the start. And what have we done? We have 5 times 17, that's 85. It's 17 minus 5 is indeed positive, so that means 17 is greater than 5. And the 17 modulo 5 is 2, so that all works. Let's do something different here now. Let's switch this. Let me stop the program, and we'll switch. Let's just switch these. So we'll go 17, and we'll go 5. Switch the order. So now we should get negative. I'm going to remove this break because I'm going to just skip through the multiply. Otherwise, we have to go through that 17 times. So I'm going to put the breakpoint right here. So that means the multiplication will already be done when we run this program again. So let's run the program. And we should look at the working registers, and we'll see that the 85 is already in there. So go down and look at the working register. Oh, I must have. Oh, sorry. I changed that as 15. Go back to 17, rerun this. Okay. Let's go down and check this. So 17 times 5, 85, still there. So we've already moved through here, so we've done the multiplication. Let's go to the compare now and just step through this. We can go a little quicker. So now we're going to step through. So notice here we skip now the is positive. We're going to look at this bit. So we're looking at bit 17. Here it is. It's a negative number, so that means that the leading bit is a 1. So this should send us to the is negative. So we'll go to the is negative, and this brings us, again, it doesn't step into here, but now we should expect a negative n here, and there's where we see that. So put in memory position register 13, we have a n. So it correctly identified that as negative or less than. Let's check modulo. This might break the module, because modulo, we don't even do it once. So this would be 5 modulo 17, which is just, of course, going to be 5. So let's step through and watch. Now this is going to be let's watch 14 change here. So we step in. So we subtract. We're already negative. So we don't go through this loop not even once, well, only once, not twice again. Add back, and we get 5. And so there we are. And so we'll go back to the main loop. Actually, I'll just stop this now. Let's do one last thing before we end this video. Let's change this to 15. This could also be a special case for that modulo. So now we're going to go, or actually, sorry, we'll go 5 here and 15. And then now we know 5 is 0, or 15 is 0 modulo 5. So let's make sure we get 0. So go ahead and I'll leave the breakpoint here. Actually, we'll just put the breakpoint right here. So we'll run. Check our file registers. And we've got 15 times 5. Here's our 75. Is positive P, so everything worked as it should. Now we will step in through here, and we'll watch our 14 change. So there it is, 15, and we're going to keep subtracting 10, 5, 0. So of course that's the answer, but it doesn't know that. So we're going to go through one more time. We go negative. Now we check bit. The most significant bit here is a 1, so we will skip that and go to add 1 back again, and there we are, 0. So even in this case where its modulo is 0, the residue is 0, then we see that it works out. So this is an example of a couple of the arithmetic things that one might want to do with the PIC10F200 if you're manipulating some kind of signal and you want the outputs to do something in response to whether something's negative or positive, or if the modulo is 0 or not. For example, if you go modulo 2, then you of course can see if something is a even or odd integer. So things like that might be useful. And here we did this all without even writing anything to a PIC10F200. We simply use the simulator tool and the debugger in that, and we were able to step through each, and it's fun to see those registers change and do what you think they should do, and if they don't, then that's a nice way to figure out what went wrong with the program. So I think we'll stop it here, and we'll get back to another video sometime soon.